In this video, we'll be discussing the apply family of functions in R. In previous sections on control flow, we discussed various looping constructs like for, while, and repeat. In addition to this, R provides a set of functions that allow for well-defined iteration through our data structures, vectors, lists, data frames, etc. These functions also allow us to apply operations or functions to each of the elements as we iterate. Now, we can certainly write or recreate all the functionality provided by the apply family of functions using the for, while, and repeat loops. But the main benefit for using these functions is that they simplify your code. In many cases, these functions remove the need to explicitly write loops and therefore help to prevent many of the common errors that occur with writing loops, and at the same time make your code more readable. So we're going to start with the apply function. The apply function operates on an array or matrix data type. It iterates over a set of dimensions that we specify and applies a function also that we specify. So for a matrix, we could instruct the apply function to iterate only over the rows of the matrix. Likewise, we could iterate over the columns. And finally, if we instructed apply to iterate over both the rows and the columns, then our chosen function will be applied to every element in the matrix individually. So to see this, let's first create a 4x4 matrix containing some values. As you probably have noticed in previous examples, the functions provided by R often can handle data types with multiple samples or multiple dimensions. That is, the functions so far haven't required us to explicitly iterate through every element in our data structure. But this is not always going to be the case. And in this example, we're going to be using the log base 2 function, which can definitely handle matrices. But I'm going to show you 3 ways that we can basically do the same operation, where the last of them is using the apply function. So hopefully with this, you'll be able to see the difference between each of the methods. And in those cases where the function you need to apply to your data does not handle or perhaps does not work with your particular data structure, then you can see how to switch from using an explicit loop to maybe using an apply statement. As I said, the log2 function works directly with matrices, so we can simply print the result of this function passing a as an argument. And we can see here that the output contains the log base 2 of every element that was in the original matrix A. So now, if we wanted to write this same operation using loops, we could use a nested pair of for loops and explicitly index both the input and output matrices. So to do this, let's start by creating a matrix B that we're going to use to store the output. And then we're going to write a for loop that iterates over each of the rows. So for I, in row of A, and we could also use the dim function here, but in row or the number of rows function makes this code more readable and hopefully more easily understood. Likewise, for the columns, we're going to write for j in call A to get the number of columns. We're using in call. And then inside the loop, finally, we're going to explicitly call the log2 function for every element in A and assign the output to the corresponding position in the matrix B, again, explicitly indexing with I and j here. And when we run this block, of course, we see that the output here matches that from the call to log2. However, we have done a lot more work to get that result. So a couple of comments here. First, the log2 function obviously handles matrices, and the for loops here are superfluous. But this is one way to use explicit loops to apply an operation to the elements of a data structure. And if you find yourself writing loops like this, especially when they can't be replaced with a single call to a function like log2, then the next example using apply will show you how you can greatly simplify this. Second comment, these loops are not terribly difficult, however, they can be a source of errors. Typos and other oversights can lead to sometimes hard to find bugs, and as an example here, I've used I and j as my indices. This is actually really common, and if these loops were to directly appear in a larger block of code that is also using the variables I and j, then these loops could modify those variables, which may not be what we wanted. One way to completely avoid many of the common issues that arise with looping structures is simply not to use them, and instead replace them with calls to functions from the apply family. Let's do that right now. So we're going to store the output from the apply in the variable b, and to call apply, we're going to pass our input matrix A. And again, the apply function is going to iterate over a set of dimensions that we specify using the margin argument, which is just a vector of indices. And in this case, we want to apply the log2 function to every element. So we're going to iterate over both the rows and the columns. So the margin vector here is going to be a vector containing the integers 1 and 2, which are the indices of the row dimension and column dimension, respectively. And then finally, we actually have to specify the function that we want called. So in this case, it's the log2 function. So I write log2, and then I'm going to print the result b. And when we run this, we see once again we get the same output as the original call to the log2 function. Now this one line of code, the apply function here, replaces the nested for loops, the explicit declaration of the output matrix including its dimension, as well as the explicit indexing of the matrices within the loop, thus avoiding any chance of typo or other error. This will make debugging much faster and easier, and it's also going to make the intent of your code much easier to identify. And so it's definitely recommended that you take some time to play with this family of functions. And when you find yourself explicitly looping through your data structures, then perhaps maybe you need to rethink your code a bit and try utilizing one of these functions. Okay, so before we move on to the next function, lapply, I want to show you one more example with apply to hopefully help you better understand the margin argument. In the previous example, in order to apply the log2 function to every element in the matrix, we needed to specify indices for both the row and column dimensions. However, if we only specified one of these indices, say index 2 for the columns, then the operation would have been applied to each column independently, instead of to each individual element. For example, if instead of using log2, we use the mean function, and we only pass the index 2 for the margin, then what we see here in the output is actually the mean of every column in the matrix. And this is because by iterating only over the columns, the input to the mean function is not an individual element as it was in the previous example, but instead it's a vector of data. That is, the input is an entire column from the input matrix A. And we see in the output, which is a vector, not a matrix, that the first value here is 2.5, which is the mean of the first column of A. If you recall, the first column of A had the values 1, 2, 3, and 4. The second value, 6.5, is the mean of the second column of A, and then so on. So by changing the set of indices passed as the margin argument, we not only change our output, but we also modify the input to the function that we have set. When we pass the indices for all the dimensions of the matrix, right, the rows and columns, the log2 function received an individual element as an argument. And when we pass only the index of the column's dimension, the mean function received a vector or column of data as input. And if you were to apply this to higher dimension arrays, then the functions you pass would need to be able to handle those input dimensions as well. Now, as we said, the apply function is meant to work with arrays and matrices. But if you wanted to operate on lists or vectors, then we would need to use lapply. The lapply function is similar to apply, except that it omits the margin argument, and really this makes sense with a list or vector since there's only one dimension in which to operate anyway. In previous notebooks, we've already seen that we can use arithmetic operators on vectors without writing explicit loops. For instance, we can multiply the sequence 1 through 5 by the value 5, and then we can print the result. And in the output, of course, we see that each of the values in the sequence has been multiplied by 5. Now we can perform the same operation using the lapply function. We're going to write lapply and then pass our sequence. And now instead of the margin argument that we needed with apply, we can directly pass our function. And in this case, the function or the operation that we want to apply is multiplication. And we can actually still use the multiplication operator here, but because it's an operator and not a function, we're going to need to wrap it with backticks or quotes in order to use it as an argument here. So I'm going to write quote, asterisk, quote. So one other thing that's different here is that in the previous examples with apply that we saw, we were using the log2 and mean functions, which both took a single argument, and they didn't need any additional argument. Multiplication, on the other hand, needs 2 arguments, and the first is going to come from our sequence, but the second will need to be set here in the argument list of lapply. So if you look at the description above, we see that after the function argument, there's a series of 3 dots. This means we can pass any number of additional arguments, and the description here states that these additional arguments will be passed directly to our function. Since we want to multiply the sequence by 5, all we need to do here is write 5 following our multiplication operator. And then, of course, we're going to print L and run the block. And in the output, we get a lot more square brackets than you were probably expecting. Well, the lapply function treats inputs as a list, and it's going to iterate through all the elements and then return the result also in a list. So what we're seeing here is a print function outputting a list with all of its different indices. The indices in the double square brackets are the list indices. Notice that there are 5, and this matches the length of our input sequence. The lines starting with the single square brackets containing 1, however, are output of vectors containing a single element. Recall that R treats all scalars as vectors of length 1. So the square bracket 1 on each of these lines is the index of the first element to appear on the line. And following that is the output of one of our input elements multiplied with 5. Now, if we don't want a list like this, there is a function called simplify to array. And if we use this here on our list L, then it will give us back a vector containing the same data, which actually matches the output at the top of the screen. So let's do one more example. This time we're going to pass a list of vectors to lapply. It may be that you have several vectors containing numeric data, and maybe you want to compute the sample quantiles for each vector independently. So let's say the vectors are v1 and v2, and we're going to assign some trivial data here. So v1 will be the sequence from 1 to 50, and for v2, we're going to use the rnorm function to generate 100 normally distributed points with mean 0 and standard deviation 1. Now, with these in place, we're going to start just as we did before with lapply. But this time, our input is going to be a list containing our two vectors here, v1 and v2. And then, of course, we're going to pass the quantile function. And now when we run this, we see once again that we get a list of output, but each element in the list is the quantile data for the corresponding input vectors. So hopefully this example helps you to understand the output from lapply a bit better. And for those instances where your output is better represented by a vector rather than a list, you can use the simplify to array function. But as this is quite common, the apply family of functions does include another function, sapply, which is really no different from lapply, except that it will automatically simplify the output to a vector whenever possible. If we copy and paste our multiplication example, and we switch to using sapply instead of lapply, we immediately get a vector as output rather than the list that we saw before. There's another function, again similar to sapply and lapply, and this one is called VApply. VApply works the same, except that it requires us to specify the data type of the output. So let's say we have two vectors of integers and we wish to get the sum of the elements in each. We know in advance that the output will be a single numeric value for each input vector. And so with VApply, just as before, we're going to pass a list of input data vectors, and then we pass the function we wish to apply, which is the sum or summation function. And last, we pass the type that we want each value in the output to be. So in this case, we can say numeric, and in parentheses, we must say how many numeric values we expect as the output from our sum function. And this is simply going to be 1, since each call to sum will add all the values that are passed to it, and then it will produce a single value as output. And so when we run this block, we see in the output that we actually get the numeric values 10 and 36 as the sum of the values in each of the vectors v1 and v2. The ability to specify the output type is actually quite useful, since now we can guarantee that if the function is successful, we have a specific type to work with in subsequent function calls. Now, the last function that I'm going to cover from the apply family is tapply. And this function applies the specified operation or function to each non-empty group of values, which are specified by an index, where the index argument is a list of one or more factors. I know there's a bit going on there, so to show you this, we'll start with a data frame containing the questionnaire data that we saw in previous section. And to remind you, this simple data set contains yes/no responses to some query that was posed to individuals of various ages living in different states. And now if we wanted to know, say, the average age of the individuals with a yes response, and then the average age of those with a no response, we could use the tapply function to do this. So I'm just going to hide the output here from the dataset block, just so we can keep the dataset variables on the screen while we write the call to tapply. So we write tapply, and our input data is going to be the age column from our data frame. Now, if you look back at the top here, The next argument to our function is going to be the index. And the index is one or more factors that have the same length as our input data. Now, we wanted to find the average age of the individuals who answered yes or no. So our index here is actually going to be our response column from the questionnaires data frame. So all we have to do is type questionnaires, $response. And now since we want the average age, the function we're going to pass is the mean function. You see, just like that, we now have the average age of those who responded no and of those who responded yes. We can actually do the same thing with our other factor column in the states. So we could replace the response column with the state column and call tapply again. So we're just going to copy and paste. And I'll change from the response column to the state column. And when we run the block, we see that in the data, there were 6 states from which the participants resided. And the output here gives us the mean age of each of those individuals by state. And for all those states that didn't have any data, we see the value NA. And the reason we see all these is if you recall from the previous example, the dataset contained individuals from 6 states, but to make our factor, we actually use the state dataset built into R to create the levels for our factors, which means we have all 50 states represented here, from which only 6 appeared in the dataset. Now, the examples given here have been fairly straightforward applications of the functions in the apply family. However, they should give you an idea on how each of these functions can be used, and I hope that you see how using these to replace explicit loops can make your code cleaner and more quickly understood by your users.